Hello everybody and welcome to Operations Research video lecture on transportation problems. And now we are on chapter 9, page 38, section called Primal Transportation Problem. Or actually that what is usually called simply a transportation problem. I call it primal here because, well, obviously we will have a dual transportation problem also. So, as usual in this course, let us start with an example. So we try to explain these transportation problems with an example. And this is the problem 9.1, and it is given in an extremely annoying form, actually on purpose. So just to make my point. So this is something like if you have a transportation problem and you have a lawyer, he will probably, or she will probably write it something like this. So let me read this out loud so we can just get into the mood, so to say. So 9.1 problem, spice must flow with highliners. So the Spacing Guild transports spice melange from Arrakis and Tleilax with its highliners. The spice is transported to Caladan, Kaitain and Gieri Prime. So in Arrakis there are 15 megatons of spice to be transported. In Tleilax there are 20 megatons of spice to be transported. So the Spacing Guild has promised to transport 17 megatons to Caladan, 8 megatons to Kaitain and 10 megatons to Gieri Prime. The shipping costs for the Spacing Guild are 3 billion solaris per megaton from Arrakis to Caladan, 4 billion solaris per megaton from Arrakis to Kaitain, and 6 billion solaris per megaton from Arrakis to Gieri Prime. The shipping costs from Tleilax are 5 billion solaris per megaton to Caladan, 7 billion solaris per megaton to Kaitain, and 5 billion solaris per megaton to Gieri Prime. So the Spacing Guild wants to minimize its transportation costs. And question is, how should the Spacing Guild transport the spice from Tleilax and Arrakis to Gieri Prime, Kaitain and Caladan? Okay, so here the problem is, of course, it's written, I suppose it's an exact problem. However, of course, this is, I would never write a problem in this way unless just to annoy you. Sorry about this. So the point is here that, of course, we would like to represent this in a better way. And one way of looking at it is actually that we are looking a network problem really here. It is a small network, but in any case. So it makes sense to write this as a network problem, at least to get an idea what's going on, and indeed this is what we have here. So this is, this is, the picture is here for us to get the picture, literally. So here we have ports, Arrakis and Tleilax, they are the green ones, and here we have the markets or destinations. So ports are also called sources. So sources are green, destinations are red. That's why the arrows here go that way. Then here 15 megaton, this is the supply of this port. 20 megaton, this is the supply of this port. And here we have Caladan 17 megaton, so this is the demand of this destination. Kaitain has a demand of 8 megaton and Gieri Prime has a demand of 10 megatons. And then the route costs here, they are given here. So for example, 3 billion solaris is the cost of transporting one unit, and unit was megaton, 1 megaton of spice from Arrakis to Caladan. Similarly, 6 billion Solaris is the price per unit from Arrakis to Giedi Prime, and so on. Okay, so I hope this picture is clear, and yeah, well, it's up to you, of course, to think any way you like. I think this is a much more nicer representation of the problem than the plain English single chapter without even any paragraphs here. All right. So what is the solution? Then the solution, of course, would be how much do we transport with each of these routes, the gray lines here, from the sources to the destinations. And yeah, of course, the associated cost is part of the solution also. And now the question is how to solve this. And before solving this, okay, so as I said, this picture is nice. I like pictures. Then I get the picture what is going on. But of course, we are going to solve this problem with GLPK, with GNU Octave. So it doesn't take in pictures, at least not yet. So we should give the problem as well, vectors and matrices there. So then it makes sense to not look at this problem here as a picture like this, but instead have a tabular form. So how do we represent this picture here in a tabular form? I mean, of course, there are many choices. I think the following one is probably the most natural. So what we do, and I will put maybe the page a bit smaller so you can see the picture and the table at the same time. Let's see if I manage. So here it is. So what happens here is that I now represent this picture here with this transportation problem table form. So I have here the sources in the rows and destinations as the columns. So this side will be the rows, this side will be the columns. Why this way? Why not the other way around? Well, why not indeed? I mean, you can have it which are rows and which are columns. It's a matter of taste. So I just now decided to do it this way with no particular reason at all. All right, so what do we then have here in the middle? What is this matrix? Well, this matrix or this table here is the transportation costs. So Arrakis to Caladan, this 3 billion Solaris, that's that line. Arrakis to Kaitain, which is this line, that's this 4 billion Solaris. And Arrakis to Giedi Prime, it's here, this line. Okay. And then Tleilax, now I'm looking at this, Tleilax to Caladan, this number here, okay, it's Tleilax to Caladan. Tleilax to Kaitain, the 7 billion Solaris there is this line, and finally this 5 billion Solaris are what? That's from Tleilax to Giedi Prime, so it's like this. So I decided to collect the data here to this table by reading the picture from the bottom to the top. So why didn't I choose first Tleilax and then Arrakis? Again, why indeed, I could have done it that way also. So obviously this tabular form is not unique, but why should it be? Okay, then the rest of the data is here in the margins. So supply for Arrakis supply is 15 megaton, as it is in the here. Tleilax supply is 20 megaton, as it is here. And then the demands are for Caladan, Kaitain and Giedi Prime 17, like here, 8, like here, and finally the demand of Giedi Prime 10 megatons is this one. All right. So indeed, now we have the problem in a tabular form. So in practice, if I would given this problem and been nice, I would have given it in this form. Okay, this is a very natural form, especially if we want to solve this with as an LP. And indeed, as I point out, this is a very, this spice, okay, there's a type of spicy. Spice must flow with highliners. This is a very typical transportation problem. And as all transportation problem, it can be modeled as an LP. And indeed, let us do so. So let us follow the algorithm 5.2. So remember this algorithm here. So it's always like this. We first find the decision variables. Once they are found, we find the objective function, and finally the constraints. Okay. So let us follow that. I think we are not page 38, but page 39 here. All right, and now usually the decision variables were the easy case, and then the objective was even easier. The constraints were difficult. Now in these transportation problems, it's maybe all of them can be very difficult, but things become relatively easy if we start with the clever trick on the transportation. Of the decision variables. And so what we do is that we define the decision variables not as a vector, but as a matrix. It somehow is natural, because if you think about this picture here, so the decision variables will be associated with these gray lines. They will be associated with how much spice will be transported with each route. And how do we represent these routes? We can do it with a vector, and in the end, or actually in some part of the solution, we have to do that. But at this point, it makes sense, or is somehow natural, to represent them as a matrix. So what is, for example, what is this line? It's line from somewhere to somewhere. So it's from Arrakis to Kaitain. So the index would be x, the number how much we transport from Arrakis to Kaitain, and then since we enumerate these, then it will be the number I associated with Kaitain, Arrakis, and number j associated with Kaitain. So I hope it's now natural. I think it's rather natural once you see it, but if you haven't seen it, it may be difficult to figure out this trick. So what I just said, I say here again. So we set xij to be the megatons of spice shipped from the source I to destination j. So these are the decision variables. So this is the step 1 of this modeling algorithm 5.2 here. And yes, we can enumerate these sources and destinations any way we like. So if we use the enumeration here that corresponds to this table, then we have these variables as follows. So note that we have 2 times 3 equals 6. We have 6 decision variables because there are 6 routes here. So x11 will be the megatons of spice shipped from Arrakis to Caladon. So corresponding this one here. x12, the megatons of spice shipped from Arrakis to Kaitain. So corresponding to this route here. And x13 is the megatons of spice shipped from Arrakis to Giedi Prime, corresponding to this route that has 6 billion solari cost per unit. So these are the x1s. x2s are the ones associated with Tleilax. So x21 is the megatons of spice shipped from Tleilax to Caladon. This one here. x22, the megatons of spice shipped from Tleilax to Kaitain, corresponding to this route cost here. And then finally, x2 is Tleilax, 3 is Kiedi Prime. So x2, 3 is the spice shipped from Tleilax to Kiedi Prime. Okay, so that was the step 1. So now we know, or we have decided what are the decision variables and how to, and we have decided to represent them as a matrix, not a vector. And related to this, yes, I should point out remark 9.2 that cleverness comes with a price. So it was very clever. Well, maybe not that clever. It was very natural to use the double indexes here, and double index meaning that we have a matrix. So we have this decision variables in matrix form, and there is a small price to pay for this. We shall see that later, but it's worth paying. In any case, those were the decision variables, and let me have these notes a bit bigger now, in the hope that it's better this way. So we started with this representation, tabular representation of the transportation problem. We are now using the algorithm 5.2, and then so here are the root costs. So for those we decide that we use the decision variables as a matrix that corresponds to this table here, and they are given here. So that was step 1. How about step 2 then? So what was the step 2 in algorithm 5.2? That was the objective. So what is the objective here? So the objective is, given the transportation problem, the objective is, yes, almost always, to minimize the transportation cost. And what is a transportation cost? So the individual transportation costs per unit for each route are given in this table. Let's call it C. So Cij is the cost per unit for transporting from source I to destination J. Okay. And now we see how convenient it was to have this Xij to denote the number, not the amount that we transport. So here it is. The objective, and this is in general form for any transportation problem. So this is to minimize the total shipping cost. So in general form it's minimize Z. Okay, we use Z here just as a symbol for it. It's a minimization, we could have used W or anything else. Let's just use Z here. And what is this? So Cij times Xij. So this is the cost we have with the route from I to J. So I and J are just indexes now. And then we have to sum up all the possible routes. What does this mean? We sum over all J and all I. Okay, this looks maybe a bit fancy. It's this kind of double sum. But this is the general form of the objective or transportation problem. So Cij is the cost per unit for this route from I to J. Xij is the amount. So this is the cost of that route. And then we want to sum up all the possible routes that they are. This means we sum from all the sources to all the destinations. Okay, this is the general form. So here the Cij, again, that's the cost of shipping 1 megaton of spice from source I to destination J. Alright, what does this mean in our problem 9.1? So what is our Cij's? And let's now write it in a matrix form. So C here is 3, 4, 6, 5, 7, 5. Where do those come from? They come from here. And let's see if I made a mistake. I make it smaller just to check. So the first row here is 3, 4, 6. 3, 4, 6, that's correct. And the second row is 5, 7, 5, 5, 7, 5. Surprisingly, I did not make a mistake at this point. Okay. So now we know what is the objective. So this is a general form for any transportation problem, and plugging in C like this and the x's like this, we get the special form in our case. So it's here. The objective is the minimized set, which is 3 times x11 plus 4 times x21. And again, here I see it's a problem. It must be 1, 1, 1, 2. Okay, so sorry about this. It's apparently I've made a problem with indices here. So this is a good time to stop, and once you get back to the next video, you will see this corrected. So obviously this is not correct. I made some mistake with the indices. So sorry about that. Maybe this is a educational moment for you. So be careful with the indices. It's very easy to make these mistakes. So I will correct the mistake, and in the next video I start with this same point.